Hello, everyone. We'll get started in a couple minutes. We'll get started as soon as Aaron is able to join as speaker. Let's see here. Okay, it took a little bit of a while last time for it to happen, so it might take a couple minutes here as well. Aaron, if you're able to accept the speaker, I don't know. There we go. Okay, I think, yeah, Aaron, everything working?
Yeah.
Okay, perfect. We will get started. I'm going to start by sharing the list of papers that we're going to cover today, which I am tweeting right now. Let's see here, and I will pin that to the top of the space. Let me do that right now. Cool. So, yeah, today we will be covering a variety of papers, I guess, from the past 2 weeks, because we did miss last week, but most of the papers are from the past week. We have about 11 papers, which is not too bad, I guess. Not too many papers, but yeah, it should be fun and interesting. We also have from one of the papers, we have one of the authors who is going to come and speak about it as well, which should be fun. So with that, I guess we will get started. The first paper, I think Aaron is going to cover this first paper, which is the Transformers or SSMs paper. So I will also pin that to the top of the space right now. Aaron, if you want to get started, feel free to start.
Yeah, awesome. Thank you. Hey, guys. So, yeah, basically, this paper presents Mamba 2, basically the next version of Mamba. Mamba 2's core layer is more efficient, scalable, and powerful than Mamba, and it's much simpler. You only need like 30 lines of code, which is super nice. And overall, Mamba 2 achieves better publicity and downstreaming performance while being faster than Transformer or Mamba. And Mamba 2 can utilize much larger state dimensions, and this is like the very important part. So it was originally like 16, but now it's like 256. And this is for like each head of their multi-head architecture. So in transformer, each dimension of each head is like 128 or 256 or 64. And as you scale up the model, you keep increasing the number of heads and making this dimension constant. And you can scale up just like that for number 2. And this dimension is very similar to transformers. And this is very important for preserving the memory. So next thing about number 2 is that they achieve this while simultaneously being much faster during training. So it dramatically improves over number 1 on tasks that require a larger state capacity. Like they tried hard associative recall tasks. Which is actually similar to copy and paste task. I don't know if you guys remember, but there was this paper that showed Mamba doesn't work well on copying and pasting task, unlike Transformer, which worked pretty well. So all that our recurrent neural network variants like RWKB and Mamba were struggling with tasks like this because their space size is very small. So they cannot really transmit a huge amount of information to the future without compressing those information too much. So basically, they solved this problem. Because these models have to compress all the past information into a fixed size memory vector, remembering longer sequences becomes almost impossible, which can affect many common ChatGPT tasks like summarization, revision, and so on. But importantly, actually, Mamba 2 performs even better than Transformer on this task, which is the most, I'd say, the most interesting part. So they essentially solved this problem. So I just talked with Chorai, the first author of this paper, this morning, and he was very intrigued by the result. But this task is very synthetic, so he's gonna try more organic task, like a actual copy and pasting of like a natural language text, or more like a actually useful tasks like summarization or something like that, and see if the same thing happens or not. He was kind of pessimistic, but it's a very interesting direction in my opinion. So yeah, if this works, then maybe Mamba 2 can completely replace Transformer, but we can't be too optimistic. So let's wait for the result. Yeah, I guess that's about it. Do you guys have any? Tanish, do you have any opinion?
Yeah, I guess yeah. So this is like, am I correct in saying like this is like for a linear transformer, right? This is not like a quadratic transformer that it is comparing it to, or what is the differences there? Is it being directly compared to like a regular quadratic self-attention transformer?
Yeah, it's just a linear attention model. So just like RWKB and Mamba. So so important thing is that increasing the memory, like a state size of linear attention, is not is actually happening like among several models, not just Mamba, but it also happened on the latest version of RWKB. So yeah, they also got performance boost from it. So yeah, it looks like this is like a common direction.
Okay, yeah, cool. Okay, that sounds great. I guess we can move on to the next paper, which is the MMLU-Pro paper. Let me invite. We have one of the authors who is here. Yeah, I will let them speak about this paper, and I will also share it to the space. Let's see here, Yubo. I think you can accept it. Let's see.
Actually, I see a co-author of RWKB paper. He can maybe give any feedback if he wants to later.
Okay, Yubo has been added. Yeah, Yubo, I've just shared the MMLU paper to the MMLU-Pro paper to the pinned it to the top of the space. Feel free to talk about it.
I think you are muted.
Hello, we can't hear you, Yubo.
Do you hear me?
Yes, now we can hear you.
Oh, yeah. Hi. Hello, everyone. I'm Yubo Wang from the University of Waterloo. Xu Guang and I are the authors of MMLU-Pro. My mentor, Wen Hu, is traveling, so we came here to share the work with you. Thanks for having me here. I'm excited to talk about MMLU-Pro. It's a new benchmark designed to evaluate language models' comprehension and reasoning capabilities. Next, I will introduce our work in 3 parts. Why did we create MMLU-Pro? What did we do, and what did we find? Please feel free to interrupt me with any questions. Okay, the first one is why did we create MMLU-Pro? It's because we noticed a few limitations with the original MMLU when doing evaluation. Firstly, as language model have improved, we have noticed a saturation in performance on the original MMLU, and it was getting hard to tell the models apart based on their scores. For example, since GPT-4 achieved 86.4% in March 2023, there hasn't been significant progress on the benchmark. Most recent models like GPT-4 Turbo, Gemini 1.5 Pro, Claude, and GPT-4o all settle at an accuracy between 86% and 87%. But models like GPT-4o indeed achieved remarkable performance boost on Mass, Chatbot Arena, and other benchmarks. The second limitation is the results on MMLU-Pro are quite unstable. It is sensitive to prompts and scoring methods. Sometimes different people testing the same model may observe an accuracy deviation of 4 to 5%. Another problem is in the MMLU, knowledge-driven questions are the majority. There are fewer questions on reasoning. Additionally, it contains some noise due to mistakenly annotated or unanswerable questions. Okay, the next part is what did we do? We started by filtering out the more trivial questions from MMLU and enriched the dataset with questions from other sources like Theorem QA, SciBench, and problems scrapped from the STEM websites. We then used the large language models to generate 6 additional distractors for each question. This turned the 4-option multiple choice question into 10 option ones. To ensure the quality of our questions and the options, we had them reviewed by 17 human experts in 2 rounds. Then what did we find? Firstly, MMLU-Pro proved to be more challenging. For instance, GPT-4o only scored 72.5% accuracy, and the performance gap between advanced models like GPT-4o and GPT-4 Turbo got bigger. It jumped from 2% on MMLU to 9% on MMLU-Pro. The second interesting finding is about train of thought. On MMLU, models generally performed better without using a COT approach. But on MMLU-Pro, our models performed clearly better with COT. Even the smaller models like the 7 billion or 8 billion models. I think this highlights the increased reasoning level in MMLU-Pro. Another finding is regarding robustness. We tested 24 different styles of prop templates and analyzed the results. Then, as shown in the paper, we plotted the results for these scores into a Gaussian distribution chart. On MMLU, the distribution looks wide and flat, which means the scores are more dispersed. On MMLU-Pro, the distribution is tall and narrow, showing that the scores are more clustered together. The distribution of scores on MMLU was much more concentrated compared to the original MMLU. It suggests that MMLU-Pro offers more consistent results across different testing conditions. So in summary, MMLU-Pro enhanced the difficulty, reasoning depth, and the robustness of evaluation. We think it's just better for checking out what these advanced models can really do. So if you are curious and want more details, please see in our paper. Our paper includes a detailed error analysis and case study of the best performing model, GPT-4o. Yeah. Thank you for your time. And do you have any questions?
Yeah, that was a really good summary of the paper. If people have questions, they can reply to the space also and put their questions there. And I will check the replies to the space and bring up any questions from there. I guess I guess I'm curious, like you said, so where so some of the questions are still coming from MMLU, is that correct? Like you said that you removed, like, I guess a lot of the easy questions, but then the hard questions from MMLU are still present in MMLU-Pro, is that correct?
Yes.
Okay, and then where are the other questions coming from? The other, because you said that you also enriched them with more questions. So what is the source of these other questions that you are adding to this data set or to this benchmark?
There are three sources. The first is Theorem QA. This is a benchmark for evaluating the STEM subjects which require the theorem to get the solution. And the second is SciBench. SciBench is another data set that includes many science questions like math, physics, chemistry, and business. And the other questions come from the STEM website named STEM EZ. We scrapped the questions from this website. Yeah, so they are the three sources of our questions.
Cool. And then, yeah, so like what are the what I guess are the models kind of struggling with right now on this benchmark? Given that the performance is much less for these models. So what like have you done an analysis of that and like what the models are struggling with?
Sorry, could you please say it again?
Yeah, like what are the LLMs kind of struggling with on this benchmark? Like, are there any patterns in the sort of questions that it's getting wrong or things like this? And just curious, like, why it's having a lower performance. Is there any sort of patterns that you've been observing?
Do you mean why the models on our benchmark is have a low performance?
Yeah, like are there any sort of like common errors that they're making, things like this?
Oh yes, we have error analysis. The most major part is the reasoning error. For example, we take the GPT-4o as the example. The issues often arise from logical inconsistency in its response, likely due to its dependence on recognizing patterns. For example, can you see our paper?
Yeah, I mean, I'm able to pull it up. I have it open up on my end, and I guess people, if they want, they can check the link as well. It's in the Twitter. Yeah, the Twitter has the quote tweet of the AK tweet, so people should be able to check there as well in order to access the paper. Yeah.
Oh, great. Great. In the appendix, we show the case study. For example, in the 19th page, there is a lack of specific knowledge case.
Oh, okay, I see this. Table 8, error analysis, case 1, lack of specific knowledge. Is that the one you're talking about?
Yeah, exactly. In this case, the model lacks financial knowledge. The cash balance for interest calculation should be the product price minus the down payment, but the model GPT-4o didn't do that. So the cash balance is calculated incorrectly.
Okay.
Yeah.
Okay.
Yeah. It's a financial knowledge, and the second one is also a case that lacking of specific knowledge.
Okay.
Yes, and another major error is reasoning errors.
Okay.
Yeah, like table 10, the model incorrectly calculate the pressure difference. We should minus the two pressure, but the model add them together. It's a reasoning error. Yeah. I suppose we also listed the calculation errors individually because we think the model developer could do the calculation.
Okay.
Yeah, we could do the calculation using the calculators or Python.
Right, right, like tool use.
Yeah.
Okay. Cool.
Yeah.
Aaron, did you have any other questions?
No, I don't have any. Thank you so much for giving a talk. Thanks for coming to the space.
Thank you so much.
Yeah, this was really great. A great summary of the paper and the benchmark. Really cool.
Yeah, we want to invite more people, more authors to space, so that they can give a short presentation as soon as they release their paper. The conventional conferences, it's like a year after the paper is actually written, which is too late. So I think this we can continue inviting more authors.
Yep, that's what we plan to do. Cool. So the next paper on our list is improving the trading of rectified flows This one I will talk a little bit about. Let me put that up on the pin that to the top of the space as well. Let's see here. Okay, so now it's been pinned. Okay, so yeah, this is an interesting paper that I guess comes from Carnegie Mellon and Microsoft, which is looking at rectified flows. So for people who are maybe not as familiar with rectified flows, it's a I guess you would maybe call it like a diffusion model formulation. There's so many different formulations these days of these diffusion models or flow matching models. So rectified flow is one of these formulations. And it's what's used, it's starting to be used by some of the state-of-the-art models. So for example, Stable Diffusion 3 used rectified flows. In the Stable Diffusion 3 paper, they actually did a very comprehensive comparison with a whole bunch of formulations of diffusion models and flow matching and found that rectified flows performed the best over all the different cases that they tested. So it is a pretty cutting edge, state of the art approach nowadays. Basically, with rectified flows, it's again similar to a lot of these models where a lot of these diffusion models where you are starting out with some sort of initial data distribution, which is usually noise, and you want to map that to your desired data distribution, which would be like the images, and in order to do that, the idea is to have some sort of ordinary differential equation that is showing you how to go from a noise to an image. And in order to do that, you need to have some function that is part of that ODE. So you have like an ODE, which is like dx dt is equal to some velocity function, and that velocity function will tell you how to move from from the noise to the images. And when you're training the model, what you're training is this sort of kind of velocity function, this or I guess you would maybe call it the flow function or whatever you want to call it. That's what you're training in order to move from the noise to the images. So this is what a rectified flow kind of does. One thing that is kind of different about rectified flows. The idea is that you want to have I guess the trajectory of your ODE of your model when you're running it, the trajectory going from noise to image should be as straight as possible. And what that allows you to do then is that you can actually sample with very little steps, because then you can kind of make very large jumps because it's going very straight. You can kind of very clearly sort of follow that straight line to your image distribution. So you don't need as many steps because your path isn't changing rapidly between the steps. So you can I guess get away with kind of lower sort of a number of steps that way. So the idea is you want your trajectory to be as straight as possible. With rectified flow, it's formulated in a way that is pretty straight from the get-go, but at the same time, they also do this sort of distillation process known as reflow, where that further straightens out the trajectories. So typically, in some of the original rectified flow papers, you iteratively apply this reflow process. And for example, the previous papers found that you had to apply it at least twice in order to get good one-step generative performance. So so you apply it at least twice, this reflow process, and then you're able to get a model that is able to generate fairly well with only one step. That said, this paper tried to more carefully analyze this reflow process, and they make the claim based on their analysis that actually you only should require one round of this reflow process, and after one round, the trajectory should be essentially, the curvature of the trajectory should be essentially zero at almost all the points in the data distribution. So like you shouldn't require more than that, more than one round of reflow because it should already be pretty straight at that point. So what they are saying is that the reason that these other papers aren't able to get it working or get best performance after only one round of this reflow process, the reason is because, you know, maybe it's not trained in the most optimal way. So they're trying to then figure out better ways of training the rectified flow model. And so they propose a couple of things. One thing that they propose is they want to they change the time step distribution. They say that the time step distribution that they use is a U-shaped time step distribution. So that is when the noise level is very high and the noise level is very low. Those are the time steps that are being sampled during the training process. So during training, you're going to be training mostly at the high noise level and the low noise level, and that kind of matches with then what is actually happening with these rectified flow models, because you know you are trying to directly predict basically data directly at the noise, you know, from the noise point, right? Because you are only taking one step. So, you know, you're starting out at noise and trying to directly predict, you know, the data. So yeah, you want to make sure that you're, you know, during trading, you're looking at that time step where you're starting out with pure noise, for example. So they have updated the types of distribution accordingly for training. And so that's one change they made. Then the other change they make is looking at the loss function itself. And so they use the pseudo-Huber loss function. So actually, you know, even in diffusion model literature, people have been trying out different loss functions apart from just, you know, the MSE loss function, you know, the L2 loss function. People have been trying L1 loss function and also pseudo-Huber loss functions. And people have been getting like different results for that. MSE, of course, seems to be pretty easy to work with, and but like pseudo-Huber loss function seems to also be doing pretty well. I think even for consistency models, for example, they were using the pseudo-Huber loss function, and that was performing quite well for that use case. So here they also tried the pseudo-Huber loss function, and this loss function is less sensitive to outliers, so it's I guess more stable to train models with this loss function. But the other thing that they do as well is they do have an LPIPS loss. So they also have a perceptual loss in there as well. And they actually have a different weighting for this. So for example, the pseudo-Huber loss is there more so when the time step is closer to 0, and the LPIPS loss is there more so when the time step is close to 1. And so they have this sort of transition from the pseudo-Huber loss to the LPIPS loss. And this new LPIPS Huber loss significantly improves the FID. So for example, on CFAR 10, you have an FID going from 5.24 to 3.38. On FFHQ, this is 7.06 to 5.21. And this is all with a one-step setting. So this is like generation, which is one step. And then the last thing that they try is basically using pre-trained diffusion models. So basically taking already existing diffusion models and then adapting it to the rectified flow formulation. Of course, there are some changes to be made with the math and everything, because yeah, the diffusion models and the rectified flow, you know, they're slightly different in the formulation. There's some changes that need to be made with some of the constants and things like this. But once you make those changes, then you can use a pre-trained diffusion model as an initialization for your rectified flow model. And then that, of course, leads to improvement in FID as well. And so at this point, it's more so now that you're kind of treating it like you're doing almost like a distillation now of your diffusion model, because you already have trained the diffusion model, and then you are then basically distilling it into this one-step rectified flow model. And so they actually perform an analysis showing that their approach is actually more computationally efficient than other diffusion distillation methods. So even though, you know, it seems a little bit maybe convoluted, it's still, I guess, more computationally efficient than some of the other distillation methods, for example, consistency distillation and some of these other approaches. So they do have an analysis in the paper for that. And then the other advantage is that because you are distilling this into what is still a neural ordinary differential equation, a neural ODE, you can do inversion where you can go from data to noise, and that is useful. A lot of these sorts of inversion, techniques can have different applications, for example, with image editing and stuff like this. So people have been doing that with diffusion models. This is also possible with rectified flow models. And the difference here is that you're able to do that with this. You're distilling this diffusion model into a rectified flow model, and you're still able to do inversion and basically then do all these sorts of like image editing and other sorts of tasks. But that wouldn't be necessarily possible with some of the other diffusion distillation methods. So yeah, that's kind of a summary of this paper, and I think it's a interesting, I guess, addition to the rectified flow literature, and I think more people will hopefully be able to use these techniques, and rectified flows may continue to gain popularity. Yeah, if there are any questions, feel free to again reply to the space, or yeah, Aaron, do you have any questions?
Yeah, so admittedly, I'm not very familiar with rectified flow. So even though I'm aware that Stability released a big paper on titled like scaling rectified flow transformers for high resolution image synthesis. So can I? And do you think that rectified flow is gonna just gradually replacing diffusion models, and or is it naive to think that like that?
Yeah, I mean, I'm pretty bullish on rectified flows. I think it's very simple to implement. It's got a very simple formulation, and like empirically it seems to do quite well. And yeah, I mean, there are some minor differences between rectified flow and diffusion models, but yeah, I mean, I think it's quite promising. Rectified flows are also the same as like flow matching and stochastic interpolance, and yeah, there's like a whole bunch of like other formulations that all kind of work out to be exactly the same, which is interesting. But yeah, I'm pretty kind of hopeful that rectified flows will gain popularity and become kind of the standard. But yeah, I mean, it's like very similar to diffusion models, and there's just like it's just about like how the functions are maybe slightly differently defined, but it's more it's easier to train, more stable, leads to better results. Yeah, so yeah, I think it's pretty promising.
That sounds very promising, very exciting. Well, when did it actually start taking off? Like, was it earlier this year?
Yeah, so like rectified flows were originally published, if I recall correctly, like fall of 2022, if I recall correctly. And then there was a paper late last year that did sort of rectified flow distillation of like a diffusion model. So they distilled one of the stable diffusion models into a rectified flow. It was called InstaFlow. And that was also pretty interesting and pretty promising. The one thing about that paper, though, is I did find it kind of odd that their distillation did require a lot of training. It required a lot of GPU hours to get the results that they got. But I think it kind of showcased the method more broadly to the world. I think more people did start to take notice of the method, and then. I guess Stability AI then started taking a look at, a whole bunch of diffusion-related methods like rectified flow and I guess flow matching and all these methods, which all kind of work out to be the same anyway. And so, then they did their own sort of empirical study of that, and based on that, decided to use it for Stable Diffusion 3. And I think that also, helped rectified flow further gain popularity. And in that case, like with Stable Diffusion 3, that's trained completely from scratch rather than doing distillation. So it is training rectified flow from scratch. And then, yeah, there have been more papers these days. Like, for example, there was one on, again, like rectified flows with diffusion transformers, or I guess there was like stochastic interpolance with diffusion transformers. that also that was kind of popular. So yeah, there have been a few papers now that have been looking at this, and I think of course the main paper that really made it popular was the stable diffusion one, but it was already slowly gaining popularity even before then. So yeah, I think it's a very interesting field.
Yeah, thank you for your clarification. I'm very excited for this this paper you're gonna present later, guiding a diffusion model with a version of itself. I guess it's gonna further improve this model, and that'll be very exciting. So okay, thank you so much. So I guess I'm gonna present the next paper, unless you have anything else to say.
Yeah, I think you can present the next paper. Yeah.
Sounds good. Okay, so my next paper is are long-LLMs a necessity for long context tasks. So basically, this paper is trying to deal with some of the long context problems using agentic approach and only using a language model with a very small context. And what this the result is that the outcome is significant improvement on question answer, few shot, and synthetic tasks. But unfortunately, they got no gain on coding and summarization tasks. And many tasks can be solved with a language model with short context, but some tasks like summarization and coding have dependencies so intertwined across the sequence that this trick is ineffective. But still, this works on surprisingly many problems, such a very strong baseline, I'd say. So, so this agentic process follows in the following process. So, firstly, the sequence is divided into a bunch of chunks, and the model reads the first chunk with this small context language model. And the model generates the action based on it, which can be one of the following: move, retrieve, append, merge, answer, or aggregation. So if it chooses a move action, then it moves to the next chunk and leaves that chunk. If it chooses retrieve action, then it uses an external retriever to retrieve a relevant chunk. If it chooses append action, and then it generates a new chunk from the current chunk only. And if it chooses merge action, then it generates a new chunk condition on all the chunks. And if it chooses answer or aggregation action, then it generates the final answer condition on all chunks. So I guess it's a bit hard to understand without looking at the figure, but basically it's just an agent deciding, making a bunch of actions at each chunk of a sequence. So actually, there are a bunch of recent papers where the model where they uses agentic approach like this to deal with very long context. For example, retrieval augmented approach is probably one of them. There are a bunch of retrieval augmented based approach to very long context models. What was the name? Well, I don't remember, but there are many of them. So, well, I guess you could say Devin and its variants could be classified as one of them because they use computer interface and agentic approach, a pipeline to sort of guide the guide the model very efficiently over a very long sequence. Yeah, so I guess that's about it. It's a very simple idea. I wanted to discuss a bit more, but I guess the thing is I'm planning to spend a lot of time presenting other papers. So yeah, that's about it. Kanish, do you have anything to say?
Okay, so they have the agentic task, and they say this approach, okay, so this approach that they have, this agentic approach, is they have like a synthetic task, right? And then they also have the just coding and summarization task as well. Yeah, I guess I'm trying to like kind of overall kind of piece everything together here. Is that about right? I guess so. You have the LLM agent that is a short context LLM agent, and it does this process like you described. That's the agent, and then they applied it to like some synthetic tasks, QA. They got improved performance, but then on coding and summarization, they didn't get improved performance. Is that basically the essence of the paper?
Yeah, exactly. So the thing is, because there are but some tasks where this approach still doesn't work, so you would still need like a very sophisticated long context model, and which is not necessarily like a brute force extension of attention span, like what people are doing, which actually it does not work well beyond certain context length. So there was this paper which essentially says that language model with extremely long context length, long attention span, actually does not use up all the attention, the context, and beyond certain lengths, the performance dramatically degrades. So there are many papers right now trying to figure out how to sort of perform long context problems very well without necessarily having to rely on brute force extension of attention span.
Okay. Yeah, so maybe like, yeah, if I guess because like, yeah, there's all these sort of maybe dependencies between sequence things like this. Is there like maybe some use of like adding some sort of like memory or something like this to the context of this LLM agent, or is there something like that that can be added, I guess?
Yeah.
Would that help?
So, well, I guess if you use Mamba2, you can consider it as a memory. But the thing is, Mamba2, even Mamba or like RNN-based models, they have limitation because, if you, the thing is, I think if you pack like one sequence of 128K tokens, then theoretically it is impossible to sort of compress everything into the state vector without affecting the performance. So yeah, memory-based approach does work to some extent. Even actually, it does have. It does not necessarily perform better than transformer, but just saying that it's like a very efficient approach. But still, there are issues like that. So some approaches actually use something like summarize each chunk. So like write a summary of each chunk.
Yeah.
Sort of like a memory,
right.
Actually, OpenAI used it to sort of summarize extremely long book into a nice summary, by summarizing each chapter separately,
Right.
and so on. So this approach seems to be gaining popularity, and that's just one approach as an agentic approach to long context problem. So yeah, I'm sure there are going to be more ideas, and I don't know which one's going to work, or
okay. Yeah. Cool. Yeah, that's very interesting. Cool. I guess anything else, Chad, or shall we move on to the next paper?
Yeah, I guess we can move on. Do you wanna? There are a few interesting people who are in the listeners. Do you wanna invite any of them to?
Yeah. Let me make you. This is. I'm just going to continue on. I'll add you as a co-host, and then you can add people if you want. But I'm just going to continue on talking about this next paper.
Yeah, sounds good.
Okay. So the next paper that I want to talk about is this zipper paper. I'll probably talk about it pretty quickly. It's just a kind of a simple idea, I guess, and they did some limited testing of it. But basically, the idea is, it's a it's like a way of creating multimodal models, I would say. And yeah, so it's the idea is they want to create multimodal models, I guess, from pre-trained unimodal decoders. So yeah, it's like generating the model. You want a model to generate different modalities, and so they have different unimodal decoders, and you want to create a multimodal model out of it, but also preserve the performance of the individual modalities. And so they have this zipper architecture. That's what they call it. It's a multi-tower decoder architecture. So basically, you have these decoders, and for example, there'll be like transformers. I think they mostly just analyze transformers here, and they are connecting these two, connecting two decoders using cross attention. And so they have cross attention that is inserted at every every few layers. I guess they have a cross attention that's inserted at between the two decoders, between the decoder backbones. And this is different from, for example, Flamingo, where they only had the final layer of like an encoder that is cross-attended with other layers of the decoder. So here they have like, they have the decoders and they have, different layers in the decoders being cross-attended with each other. And so yeah, like that's all it really is. It's a very, very simple idea. And yeah, they did. I mean, I was just interested because it's kind of interesting to explore some of these multimodal ideas here. And yeah, like it's a very simple idea. The thing is they only tested it out with basically text and speech modalities. So yeah, it's a little bit hard to evaluate how well this method works. And they didn't even release any sort of like samples of the speech generation or things like this, or even the speech to text, or the speech to text and the text to speech. They didn't release many examples of that either. So it's really hard to tell. But basically, what they did is that they had like POM2 as the text decoder, the text backbone, and then they have a similar sort of decoder only architecture similar to POM2 for the speech backbone, and it's they have like a speech tokenizer that they have, and you have these speech tokens, and your speech decoder is basically still also doing next token prediction, but with these speech tokens. And so they have these two models. Both are quite similar with each other, but they are for different modalities, and then they apply their zipper approach to that. And then the speech backbone is pre-trained on unlabeled speech data. They have like 60,000 hours of data, and then they take their zipper model and then they train it on a couple of tasks such as speech to text and text to speech. And the advantage of their approach that they're claiming is that you don't have to use a lot of paired or aligned data. They used, for example, as little as 1% of the text speech aligned data, and we're still getting good results. And yeah, so I think that's kind of the general idea. But it's an interesting idea. But ideally, I think it would be best if they had tested it on maybe more modalities and more. Yeah, I think the results were a little bit limited, but overall still interesting. Any questions, I guess?
Yeah. So actually, I recently posted a very similar a question very similar to this topic on Twitter, and
okay.
yeah, so, and one of the people suggested me this paper. I wasn't aware, so such
okay.
topic. So the thing is, for multimodal models like this, there are two main approaches. One is self-attention based approach. Essentially, you have a bunch of different modalities, and you use encoders or just tokenizer to sort of feed every data into one single unified language model. Yeah, that's okay. That's self-attention based approach. And another one is like this one, like Flamingo or all these models that uses modality specific model for each modality, and let them communicate with each other via cross attention. And the responses I got from a bunch of people is that cross attention based approaches tend to perform worse than self attention approach. Actually, there was like a rigorous benchmarking evaluation. So, but actually, it seems like the result depends on like some settings. Like if you are dealing with like image text, standard image text problem, then typically self attention performs much better than cross attention. But I guess given that this paper is specifically about audio and text, I guess it doesn't. Probably it doesn't really matter. But so the thing is, I was originally very leaning toward the use of modality-specific models over unified self-attention model because, when you are dealing with multimodal data, so if you're dealing with video, then when you process videos, it takes many time steps, right? Compared with text, like each frame takes up like 64 times tokens or something like that, which is very expensive. So, and you don't want to use gigantic large language models like 70 billion models to process all these time steps. So I wanted to use something smaller for video and something larger for text so that we can save compute. But apparently that may not work according to those people based on their experience. So I'm very curious about what's going to happen. Sorry if that makes sense.
Yeah, I guess that makes sense. I guess I'm curious because this paper, I think one of their selling points was, or what they were hoping is one of their selling points is that I think the idea of you don't have to use as much paired data for these tasks. You can just do this sort of unsupervised pre-training on the separate modalities. On so if you have a lot of unpaired kind of data for all these sorts of other things, like they have like a lot of speech data, a lot of text data. And then you don't have to. Then you can use very little aligned data. Then that's I think what they're trying to sell this on in terms of like what they want to, that this architecture enables that and gives you good performance in those scenarios. So maybe that's where this will shine. And I don't know if people have done similar experiments with like these self-attention architectures. And if I don't know if you've seen anything like that where people have done that sort of analysis. But maybe that's kind of what this would be best for. But if you do have the data to train on, like for the supervised task, then maybe it's better to do, the self-attention. So maybe that's kind of the distinction there.
Makes sense. Thank you.
Cool. Yeah, is there any? I guess I tried adding you as a co-host, but I don't know if you're not being added. But is there anyone you wanted to invite up? I guess or.
Are you asking me?
No.
Oh,
yeah.
Sorry, I'm the only one. Yeah, let's see. I just see two people on the top of the column, Alex and Yam.
Okay, yeah. You can invite them if they are interested in speaking.
Yeah.
And then also I guess we can move on to the next paper, which I think the next paper you will cover.
Yeah. Okay, so I'm gonna talk about FineWeb. Probably many of you already know. This was released by Hugging Face. Basically, like very 15 trillion tokens open source dataset with very permissive license, and it's a very high quality data. So yeah, it's for pre-training large language model. So let's see. Yeah, so it was derived from 96 common crowd snapshots. So it's a large fraction of common crowd. and it produces better performing large language models than any other open pre-training datasets. And the license is called ODC by 1.0. It seems very permissive. And they also presented FineWeb Edu. It's a subset of FineWeb constructed using scalable automated high-quality annotations for educational value. And it performs all openly accessible web datasets on a number of educational benchmarks like MMLU, ARC, and OpenBookQA. And FineWeb Edu is available in two sizes, 1.3 trillion and 5.4 trillion. So as for how they built these datasets, they first used DataTube. And so they basically use DataTube, which is like a data cleaning, data pipeline tool they recently open sourced. It basically allows a seamless scale. Basically, they do seamlessly scale filtering and dedication set up to thousands of CPU cores. So the process is like this. Firstly, they do URL filtering, like a dedication and removing unwanted URLs, and then which is a very standard process. And then they do text extraction. So essentially, this step is that they process work files from Common Cloud instead of using web files. So web file is like an already processed version of work, but they process it. Common Cloud people processed it, but that's in a very outdated way, or like a very like a suboptimal way. So there are a bunch of better ways to process work files into text format for language model training. So they basically used it. And this, and then they used language filtering. So basically here they removed adult content and used fast language classifier to sort of remove like a very, probably like a, I think they sort of probably removed some weird results, I guess. And then they also did quality and repetition filters for massive text. And then after that, they did dedication, and they used min hash, which is a fuzzy hash based dedication technique that scales efficiently to many CPU nodes. And actually, interestingly, they found that too much dedication leads to worse performance. And as for the reason, they think that as filtering gets more strict, the benefit from filtering is lost, and the destruction of the original data distribution due to filtering becomes more and more apparent. Yeah. So don't do too much dedication. Actually, moderate amount of it is just enough. And then they performed additional quality filterings. Like actually, they used all the filterings used for C4 paper and plus extra. So yeah. Then finally, they so that's the last step basically. And then they trained language model on this and compared it against the same model trained on a bunch of other open source datasets. And then they, as you guys probably have seen in Twitter post, like the performance of FineWeb was much better than all the other datasets. And also FineWeb Edu version, the gap was even farther away. So that was great. Yeah, I guess that's about it. Any question?
Yeah, so I guess what aspects of it are the ones that are, I guess, it's unclear to me what, I guess it's just, highly filtered, but like, I guess there are many other sort of continued open pre-trained datasets that have also been, pretty filtered. So I guess there were a couple of things about the deduplication and some of these things, but I'm curious if there are any like one technique that really improved the improve the data set here, or is there anything that really stands out, I guess?
Let's see. Yeah, it's really like if you take a look at each the web blog post, I don't really see anything that particularly stands out. So I'd say this paper is more like combining best practice at each dimension.
Right.
Yeah, more incremental work. So, but this their finding of deduplication, too much deduplication leads to bad performance. Maybe something to remember, I guess.
Right. Okay. Yeah, that sounds cool.
Yeah. So yeah, basically, these incremental improvements often lead to significant final performance improvement. That's a very important takeaway, I guess.
Yeah. Cool. I guess anything else you want to add, or I guess we'll move on to the next paper?
Yeah, I guess that's about it. It's a very simple paper. So yeah, that's all.
Cool. Okay, so the next paper is offline regularized reinforcement learning for large language models alignment. Let me put that up on the space, pin it to the space, and then let's see here, and I will talk about it. Okay, so I've pinned it to the space. This is a paper from Google DeepMind. And the idea of this paper is that like looking at kind of like preference learning for language models, of course, as these models are getting better, it's hard to kind of distinguish between, a pair of responses, which one is better. And like just overall, the idea of like annotating pairwise data, like that's kind of like less natural in a way, and it's more expensive to get. The idea is like typically it's just easier to just say if something is good or not. For example, I guess that's maybe something that's easier to collect. So like, I mean, you see it even in some of these language model interfaces right now. You can just give it a thumbs up or a thumbs down if you like the response or you don't. And so the question is, can we use that data to directly optimize a model? So they call that sort of data single trajectory data, where you have like the single trajectory of a model response and sort of preference, or not. I guess it's not really preference, or it's just like a kind of some sort of value associated with it. So they have the single trajectory data. They are their paper is about how to perform single trajectory RLHF optimization, and they call that they call their framework for this direct reward optimization. And they mentioned that there are very few offline alignment methods that consider this setting, with the exception of KTO, which is Kahneman-Tversky optimization. I've heard of that paper before, and I've seen it a little bit. I honestly haven't, very comprehensively read that paper, unfortunately. So, but I think it seems like this is one of the few other papers that actually analyze a similar setting. It seems, and they actually directly compared their results to this method. So yeah, basically, they just it's a pretty simple approach that they take. I mean, they like construct their policy gradients. Pretty I guess for an RL person probably be pretty straightforward. They do have a value function in there, and so they have a loss function that you're jointly optimizing over the policy and the value functions. The policy being the language model, and then you have a value function. So you have like a separate policy gradient, and you also have a gradient for your value function and optimizing your value function. And what they empirically what they show is that like counterintuitively, I guess, you need separate networks for the language model and the value function. So I know like some of these papers or some of these methods when they are having a value function in their optimization, like it will be sort of part of the same model, and it's like a head that they have of the same model. You add a head to the model that predicts the value function. Here they're saying that you have to have a separate model altogether, and that seems to work better empirically. And so for the experiments, they were looking at the ultra feedback data set, and they were using T5 language models, and then they used POM2 as an LLM judge. And then based on that, they show that their approach outperforms KTO both with a T5L model and a T5XL model. But yeah, that's kind of this paper in a nutshell. It's I guess a kind of a bit of a more theoretical paper in terms of like going over the math about this, and then also they do a few experiments, but it's admittedly pretty limited, especially for a Google DeepMind paper, which is kind of interesting. In fact, if I recall correctly, I think they said they like ran this on a sync. Well, no, actually, no. This was a run on like I think this was run on TPUs, but still, like I think this is a pretty limited sort of results. Unfortunately, I think the idea is very interesting of using the sort of single trajectory data and doing this in an offline manner and constructing a framework and a method to do that. But yeah, it's unclear if such a method would compare well to if just training with DPO, and yeah, the experiments are quite limited. So yeah, I don't know. It's very interesting to see these papers come out of DeepMind, Google DeepMind. I think people like to say like the papers these are the sorts of papers they come out because they don't actually work in practice. So I don't know if this maybe it's just one of those sorts of papers they publish it because it's not something they're using internally, I guess, and they just publish it. So maybe take these results with a grain of salt, I guess. But it's certainly something maybe to explore further, and maybe hopefully there'll be some follow-up papers that do a more comprehensive analysis. Yeah, Aaron, do you have any questions?
Not really. Yeah. Yeah.
Okay. Yeah, and again, just a reminder: if people want to ask questions, feel free to reply to the space. And I think you can like press in the bottom right corner. You can press on that with the sort of, I guess, speech bubble or whatever, and you can reply to the space there. So if you have any questions or comments or things like that, feel free to reply and add it there. But yeah, if Aaron, you don't have any questions, I think we will move on to the next paper. I think I'm actually covering the next couple papers. Let me check here. Yeah, I guess I'll cover. Yeah, I'm covering 3 more papers, and then you will cover the last thing. So yeah, let me cover the next couple papers as well. The next paper is transformers can do arithmetic. Yeah, transformers can do arithmetic with the right embeddings. So let me pin that again to the top of the space. Okay, I have pinned it to the top of the space. So yeah, this paper is a paper that is, I guess, addressing a very interesting question. So, people have been talking about like how transformers cannot do arithmetic and that they keep struggling with it. This paper tries to address that a little bit. And so basically, the overall idea here is that, the hypothesis is that the reason that these models aren't able to do well with arithmetic is basically because the models aren't able to represent the exact position of a digit within like a long sequence of digits. So they don't really know how the digits align very well. Like, so if you're adding 2 numbers, they don't know how the digits align between the 2 numbers. So this makes it very hard for them to be able to perform arithmetic. And so they propose a variety of different things. The main thing that they propose is this abacus embeddings. Basically, it's a very simple idea. It's just saying like you have embeddings that encode the position um, uh, for each digit in a number. So, for example, like you have like if your first number is 1, 2, 3, 4, and your second number is 5, 6, 7, 8, then you'll have kind of a uh, embedding, like a one embedding for the digits 1 and the digits in the first number, and the digits 5 in the second number. Then you have like some sort of 2 position embedding for the digits 2 in the first number and the digits 6 in the second number, and you kind of continue. So like the idea is that the position embeddings kind of match up between the same digits in the different numbers, and that's kind of the basic idea. The other aspect is that in order for this to kind of generalize better, what they do is they're not really just starting out of like you have 1 and 2, like you're always starting out from 1 during training. For training, they actually start out like with a random offset value for the position embeddings. So there'll be you choose some random value like 10 for the position embedding, and then the position embeddings will then be consecutive for the remaining digits, is 10, 11, 12, 13, or something like that. And then there'll be, these are learned position embeddings. So you have like a 10 position embedding, but of course that corresponds to some actual embedding that's being learned. And the idea is, of course, here that with the random kind of chosen offset value, then this generalizes well during test time to, sort of out of distribution. If it's, you may train with certain number of digits, but they should be able to generalize to more or less of that number of digits, for example. So that's their idea. And then they have a couple of other tricks, which it kind of makes them more like, honestly, like architectural changes to a certain extent. Yeah, so they have like changes like, for example, they have like input injection, which is like these sort of skip connections that provide a copy of the input to each layer of the network. So this is like, yeah, it's kind of like almost like an architectural change, to be honest. And then they also do like recurrence. So they actually kind of, you know, they have like some of the transformer blocks, but then they like keep feeding it in back into each other. And so they have like recurrence, and they have this sort of, I guess they call it a looped transformer. So they have all these other tricks as well. And they're able to get near perfect accuracy for some of these tasks, some of the arithmetic tasks, with addition, and then like most of the papers previously have been analyzing addition, but then they also try some other tasks like multiplication, and their approach seems to work well for that as well. So they achieve near perfect accuracy in distribution for multiplication, and also higher accuracy for 15-digit multiplication than prior work. So yeah, like overall, this is quite interesting. They also combine this with rope, and that yields improvement in like generalization with different lengths, for example. But I think it's this idea of like looped transformer and recurrence, that kind of like then is a little bit iffy, because like now it's not really just like a pure transformer architecture. There are some other changes to it as well. But overall, yeah, it's I think a very interesting idea, and I think it's a significant progress in this area. Yeah, that's all I had to say about that. I think Yam, you want to maybe speak?
Oh yeah, fine. How are you doing? I worked on this exact setup, I think 2 years ago. So I could just share that what I found, obviously the paper is way more advanced than that. It's been 2 years. Anyway, the thing is that transformers and language models in general are pretty surprisingly well when you try to extrapolate beyond the context length if you don't use any positional encoding. Just out of the box, they are really great. There was a paper that termed the term nope, like rope, that is no positional encoding, nope, and it works really well on this setup where you just learn arithmetic over and try to extrapolate. The thing is that rope and all the modern positional encodings work really, really well inside the length that you trained. This is why we use them. They're not a little bit better, they are way better. If you look at the loss, I mean, it's not in the same ballpark. Anyway, so this paper, and there was another one, I think a month ago, are the papers that try to find ways and tricks to get this ability of extrapolation to longer length to the modern positional encoding. That's the whole trick. And I really like this paper, by the way. They went thoroughly through many different methods and watched what happened, like one experiment after the other. And it's a really great paper. Yeah, so highly recommend reading it if you're interested in extrapolating to longer context or infinite context. If you're dreaming about this, really good paper.
I guess, do you have any thoughts on this idea of input injection and loop transformers?
I think that it's interesting that they saw improvements when changing the architecture itself. This is a little bit surprising to me, I must say, but yeah, I mean, results are results. So maybe we should consider.
Okay, yeah, cool, yeah. Aaron, did you have anything you wanted to add or any questions?
Oh yeah. So I don't think I can say anything interesting here because I'm a fundamentalist of like using two using two whenever possible. So so if you could use two well, you can maybe those algorithms can generalize well as well. So, but yeah, generally speaking, this kind of using embedding to sort of deal with numbers, and those are very interesting too. Like GPT-4's tokenizer, ChatGPT tokenizer was using like assigning each vocabulary from 1 to 1,000 integers. And on the other hand, Llama tokenizer was using like assigning, they're separating all the digits, like 1, 2, and so on. So, and obviously Llama tokenizer generalized works much better, and GPT-4 sometimes works a bit weird because of that. Maybe it's not a big problem, but a few years ago, our tokenizers were very bad with respect to digits, so there have been some improvements. And I guess this one is going to be like a next iteration, maybe. And yeah, so I guess that's very interesting.
Cool. Yeah. I'll move on to the next paper, which is, let me check here. The next paper is, the guiding a diffusion model with a bad version of itself. I think a lot of people were interested in this paper as well. I think it's a very interesting paper. Okay, cool. So this paper is from Karas et al. They're a group of researchers at NVIDIA. They are honestly, some of the best researchers in generative AI. They previously developed StyleGAN. They invented StyleGAN, and so they did a lot of interesting work in the GAN literature. And then they moved on to diffusion models. They published, they had their first Karas et al. Paper, I think summer of 2022, where they basically, introduced a very clean formulation for diffusion models and a variety of, training changes and a whole bunch of sort of like just basically a kind of a good framework for creating diffusion models. It was a very impactful paper. It was, honestly, one of my favorite diffusion papers of all time. And then they published end of last year, I think, another paper which looked more at sort of the training dynamics and modifying the diffusion model architecture to improve training stability and convergence. And so they had that paper as well. They also had a few other tricks, for example, tricks with the exponential moving average during trading and a few other tricks as well. And so that was another really interesting paper. And now they have this paper, which is less, I would say, I guess maybe less comprehensive and more just kind of based on focused on a very simple idea, I guess. And what they're focusing here is on classifier free guidance. So maybe some of you are aware of classifier free guidance. Basically, it's a trick that is used in diffusion models to basically improve their performance with conditional generation. So the basic idea is that you have your conditional model, and that kind of, I guess, provides you you have your diffusion model, and it's okay. So yeah, I guess before going to conditional model, you just have like a regular diffusion model, and maybe it's in this case, like let's say it's unconditional, it's generating for an entire data distribution, and it's giving you predictions of how to move forward to the data distribution. On top of that, you can do something called classifier guidance, which is where you may have some sort of classifier that's giving you like it's telling you the exact class of an image or something, for example, and you can use that to kind of guide the model. You kind of add that gradient of that classifier to the prediction. So you're trying to move in a direction that increases the class of the class that you want. And then on top of that, you have, so the problem with that, of course, is you have a separate classifier to do that. The trick with classifier-free guidance is essentially you're trying to basically construct what is a class, like a classifier out of your generative model, and you get you basically are doing everything with the same model, and so you have this sort of classifier-free guidance because you don't have to have an external classifier. So that's what you have, classifier-free guidance. It's used basically in all the diffusion models that we have, the state-of-the-art diffusion models. And this paper is analyzing sort of, the sort of inference of these models and looking at, what makes classifier-free guidance work and the issues with classifier-free guidance. Because the problem with classifier-free guidance is that it's very good at generating high quality images with a particular class, but it loses diversity in samples. And so, it's kind of very concentrated in terms of like the data distribution. It'll be very concentrated for the specific classes. Whereas with a regular diffusion model, it's going to be more, it'll have more diversity, but each image itself may not have the highest quality. So what they observe specifically is that they look at these diffusion models. They show that when you're training a regular diffusion model with score matching, with this typical loss, this tends to try to cover. It's trying to cover the entire data distribution, and it's trying to learn the entire data distribution. But the entire data distribution also includes some low probability regions, and that will be somewhat overemphasized, and so it leads to outliers. And so you'll get some outlier images that may not be so good and may not look so good. But classifier-free guidance, it's giving you a gradient that is pulling closer to the core of the manifold, to the core of the data distribution, and so you don't have as many of these outlier samples. But it's not going to give you a very good diversity. And like overall, what they realize is that like if you have an unconditional model, that model is trying to generate from all the classes at once, right? And it's doing so with a fixed training budget. Whereas if you have a conditional model, it's able to learn for the specific classes, and it's able to learn with the specific classes and able to kind of learn the gradients for those specific classes a bit better. And so like their hypothesis overall is that the unconditional model just overall has a worse fit of the data, and it's covering more outliers and things like this. whereas your class conditional model is able to it's able to get the core of the data distribution very well, but then it completely misses the outside of the data distribution, or like the less lower probability regions. So the idea is that, okay, we don't want the unconditional model, we want just a class conditional model, or I say class conditional, it can also be text conditional, so like text to image, for example, as well. So you have a conditional model, but how can we do guidance with just that one model? Well, the idea is that you can try to use a weaker version of the same model. And so it will have sort of similar errors in the same regions. But it still will have that worse fit that you have the unconditional model. And like the overall idea is that the unconditional model has a worse fit of the data distribution, and the class conditional model has a better fit for those specific classes. And like with classifier-free guidance, you're kind of taking the difference between that and kind of highlighting that difference. And you're trying to avoid the areas with the worst fit and go towards the areas with the better fit. And so if you have just a worse version of the same model that also has a worse fit, then you should be able to achieve a similar sort of result, I guess. And so they do a few experiments to test this out, where, for example, they take an existing model, and that existing model is trained on ImageNet 512. That model gives an FID of 2.56. Then they add 5% dropout to it, and that gives you 4.98 FID. And then they have a separate model with 10% dropout that gives you 15 FID on this ImageNet 512 dataset. And then you can use the 5% dropout model and the 10% dropout model. So the 5% dropout model is the better model, the 10% dropout model is the worst model, and you can use this sort of auto guidance process to generate, and that gives you 2.55 FID. So it's basically you've gone back up to the regular FID based on this idea of having worse, a model with a worse fit to the data, kind of taking the difference between a model with a better fit and worse fit, and that's what the auto guidance is doing. And so they do also. Yeah. Oh, sorry. I'm just talking away. Sorry.
Jan wanna speak.
Yeah. Go ahead, Jan.
Yeah, my question is, if you already have, I don't know, you just make worse models with dropout, and that they are worse because you test them on a test set. I mean, it sounds like at the end like exponential moving average, where you at the middle of the training take snapshots and then just push your model vector wise to the direction of the difference between the two. It helps during training. I mean, can't you just do it to the weights at the end if it's the same model? It sounds like ensembling. I'm not sure that.
Yeah.
Maybe I don't understand well enough the classifier free intuition behind it, but I don't know. Maybe you can do it.
Yeah, no, you're right. I think there's a lot of similarity there. But I guess what I was, kind of going into the results a bit, like, the idea of like this sort of like making the same model worse. What they say is like, this is a very like synthetic scenario, and that in actuality that doesn't work. So what they actually do is so it doesn't work for, like, I guess more generally for like larger models and things like this. But for the, an actual scenario, what they do is they take they have like a big model. So for example, they have like this EDM2 XXL model. That's their largest model. And then for the worst model, what they do is they actually choose a smaller model. So they have EDM2 medium, and that model was trained only, I guess they choose a weird thing of like 1 out of 3/5 of the training time, and I guess they empirically, tested that out. But yeah, so like, I guess you could like, yeah, they're actually using like different size models here, but the model was trained on the same data. They're just actually using different size models. But the trading is like the trading sort of setup is pretty much very similar between the two models. And so that's one thing that they're showing. But I think apart from that, if you were to use like different, just from this like the same size model, but like different parts of the training, like an earlier checkpoint, for example, then yeah, I would agree that would be very much similar to EMA in that sense. But yeah, this is
actually using smaller model for classifier free is smart. I mean that's a really cool idea.
Yeah.
So yeah,
Yeah.
I mean it's like doing the speculative decoding, but for
Yes.
images in sort
Yeah.
of way. But yeah, it's
Yeah.
really,
Yeah. I
that's
see
a really
that.
cool
Yeah.
idea. Yeah.
Yeah. In subsets, yeah, that's pretty much kind of what it is. Yeah, and the thing is like yeah, the other aspect is because like with classifier free guidance, you did have to do basically two forward passes of the same model, right? In this case, you are going to have to do two passes of the model, but one model is smaller. So also you do save some computation as well with this approach. And so that's the other kind of benefit as well. But yeah, that's the other aspect. So yeah, they achieved new state of the art. So actually, even like I mentioned, they use this XXL model, which is their biggest model. But then they actually had some small models. So they had an EDM2S and EDM, which was their base model, and then EDM2XS, which is like an extra small model, which they use as their worst model. And they use this auto guidance with that, and that brought the FID from 2.56 to 1.34. That already was that already achieves state of the art for ImageNet 512. And then the XSL and the medium one gives even better results of FID of 1.25, and that's even better. But yeah, like it seems to be a very powerful technique. And yeah, they tested on ImageNet, I guess 512, but they also tested on it tested on like a 64 by 64, but like someone was pointing out, which I kind of agree, like measuring FID on that is a little bit like I don't know, iffy in my opinion, because like I don't know, it's but like yeah, anyway, uh, overall, I think it's a very interesting method. They also finally did try with a text-to-image model. They tried with deep void IF. The reason they tried that is because there are different model sizes that are available, so they can try this idea of like a larger model and versus a small model. But they only show qualitative results. They don't have any quantitative results for that, unfortunately. But they did see some really interesting qualitative results, and it was getting better. And like overall, with the results qualitatively, you can see like the diversity is better. It doesn't like with classifier free guidance, because it's so like it loses its diversity. So kind of in some sense, it's almost like a mode collapse. It kind of like focuses on kind of canonical images in a sense, and it's like you lose that diversity. So with their approach, you can kind of see some of that diversity. You can get some of that diversity back, and so they were showing that in their qualitative results as well. But yeah, that's kind of the overall approach.
So I have some comment on this. Actually, so you guys suggested that exponential moving average, this approach, and classifier free guidance, they all belong to the same family. Totally agreed. And actually, similar approaches were already tried on language model. And the language model counterpart of this proposed approach is known as contrastive decoding. And it does work well to some extent, but not actually the performance improvement is much smaller than this approach on image. The reason why is that actually you can guess why this happens. So if you think about it, exponential moving average performs pretty well on image models or diffusion models compared with text models. And actually, people used to try EMA on language model, but stopped doing it because it doesn't work that well. Likewise, for classifier-free guidance, actually, Electro AI released a paper about it for language model. It worked. It led to some improvement, but not quite that good enough to be sort of go mainstream. So yeah, that's basically the historical, basically like a additional background. And go ahead.
Yeah, I mean, I just like the general concept of using a smaller model for classifier free diffusion. and I think it has a lot of potential, even if I don't know, we don't have benchmarks or just the idea, this direction. I didn't think about it, and I think it's great, and yeah, I also experimented with exponential moving averages during training of LLMs, and yeah, just like you say, it doesn't help that much. But yeah, cool.
Yeah, I guess if you are talking about training phase, then you could say that Adam is, using EMA on a gradient, or
Yeah, yeah.
so. Yeah, that's about it, I guess.
Cool. Yeah, okay. I guess we'll move on to the next paper. We've got two more papers before we're done. I cover one last paper, and Arun will cover one last paper. So yeah, with that, I will move to the last paper that I will cover, which is self-improving robust preference optimization. Let me pin that to the space. So this paper is a paper from Cohere. It's a very, again, another, I think, an interesting idea for how to do preference optimization, focusing on trying to self-improve. And so the idea is actually quite simple. The idea is to have kind of like, I'm going to say two models, but we'll get to that in a bit. The idea is to have two models. One model is a self-improving model. So what the self-improving model does is that you have your preference data set. You're training a language model on this preference data set. Basically, you're giving the language model the prompt, the response, and given the prompt and response, the self-improving model should output the better response. So basically, yeah, like if you have your preference data set, you take your prompt and then you take the response that has the worst preference, is least preferred, and then that's the input for your LLM, and then the output that you train against, the ground truth that you train against, would be the preferred response. And so the idea is that you're going to have a language model that's going to learn how to take a response and improve upon it. And so they call this in-context self-improving model, because you have the context of the prompt and you got the response, and now it's going to output the better response. So they have that aspect. They also have aspect of, okay, now that you have the self-improving model, train the LLM to generate responses that cannot be further improved by the self-improving model. So that is how you try to kind of maximize the performance of your language model and maximize the quality of the generations of your language models. And so in some sense, this is like a min-max optimization, kind of reminiscent of, again, adversarial kind of trading here, where you have a model that is trying to not necessarily discriminate, but like not, I guess it is kind of discriminating. But not just discriminating. It's like it's trying to make a better response, I guess. And then you have the model that is trying to generate the better response from the get-go, and have a model, then have the other model cannot really improve upon it. And so it's kind of like a min-max thing. And actually, yeah, so these objectives are actually trained simultaneously. So the thing is, like, you can actually construct this as a sort of a single kind of loss function that can be trained simultaneously. So it doesn't have to be trained separately. You don't even need to have separate language models. So that's the other thing. I did say two language models, but actually it can be trained with the same language models, with one single language model. And so you just basically it's even though it's like the sort of min-max sort of kind of optimization, and these sort of two kind of tasks that you're training, you can actually combine them and train them with a single loss and a single LLM. And yeah, actually it comes out to be a pretty simple kind of supervised loss, I would say. And then yeah, they did some simple experiments. I really like the idea, but I'm going to say that the experiments are, I guess maybe before I move on to the experiments, maybe Yam, you want to say something?
Yeah, look, There are, it's interesting because there are several papers that are experimenting with like iterative improvements and so on. Look, in general, when you use a reward model, it's pretty much the same thing as using a discriminator and you're optimizing based on it. The thing about this is that you are not just discriminating between which response is better. You are, because it's in the context, you are actually generating like the better response. And
Yeah.
just from another paper, I think by Meta, a couple of months back, where they collected data from the internet and just used an LLM to generate like a fake prompt that this data would have been the result of, and then filtered only things that that made sense. What they discovered is that only simply by doing this and filtering well, if you use the same model and do this iteratively, it gets way better. Also on the task of this and everything else, because the instruction and response align with each other. So I think that on this paper, if, just like you said, if you use the same model, both for discrimination and for the generation or improvements, you're going to get, it's going to be much better than using two models. I think that like these two abilities pretty much intertwine. If you can distinguish between what is better, it probably helps you to also generate a better response in a sense. So
yeah. Cool. Yeah. So going to the experiments, yes, I think it's a really great idea. It's very interesting. The experiments are a little bit lacking, unfortunately, though. They basically train a Llama 7B model. So I think this is like, yeah, Llama 7B, not even Llama 2, if I think. It's like not even Llama 2. And then they trained this on summarization data sets. Or I guess the Reddit TLDR summarization data set specifically. I think that's, this was a data set like from 2020. I think this was released by OpenAI, if I'm not mistaken. But yeah, this is a kind of a an old summarization data set that they had that's been used for some of these experiments before, RLHF sort of stuff. But anyway, they that's what they tested on, and then they also had a separate data set, XSum, another summarization data set, and this is sort of their sort of out of distribution test. So they're looking at how well the model generalizes out of distribution. And so, yeah, they train, of course they do supervised fine tuning at first, and then they perform their SRPO. They also compare to DPO and also another method called IPO. I think it's identity preference optimization. And then for evaluation, they basically use Alpaca Farm for automated evaluation with GPT-4 and looking at the win rate between the methods. They are getting some benefit with their method, and the benefit is more apparent, I think, with the out of distribution. So that's what they're highlighting more, is that this doesn't work well with the out of distribution case. And yeah, they are actually doing like multiple sort of revisions. So like you don't just train it once, you train it, you do this process a couple times. I guess they do it up to 5 times here, where you I guess you start out with the final train model and then again continue on. But yeah, like, so that's kind of the idea. I think the idea is very interesting, but these experiments to me seem a little bit limited. So I don't know if we can make a very strong conclusion about if this method works or anything like this. But hopefully there'll be more experiments in the future about this. Yeah. Jan, Aaron, anything you want to say? Anything you want to add?
Yeah.
Or questions?
I totally agree with you in terms of like experiments and results. But I really like the idea of like a in context improvement that they considered. That's definitely going to be like a key ingredient to that, like whatever future language models or agent and so on. Because when you play, say, video games, you have to keep improving within the context, maybe. So that kind of process going to be very useful for many different cases, not just like a language model too. So yeah, hopefully it's going to work. Yeah.
Yeah, I think I totally agree with you. I think that the methods of just improving between pairs of responses, that one is better than the other. I mean, you don't have the signal of what exactly you need to respond. We just imply that with enough examples, the signal would emerge and the model will move to the correct direction. And the whole process of generating an actual better response, or even giving a model a pair and asking it what is the thing that made this respond better than the other, is a signal that it's great to see that this signal is starting to get embedded into this process, because obviously it's natural. I mean, at the end of the day, it's a really important signal, like what to improve. So yeah, I totally agree with you that the whole idea is very promising, even if we don't have experimental results at the moment. Yeah.
Cool. I think with that, we'll let Aaron do the final paper, which is, I guess it's more of a kind of a, I don't know, what, like a report. I don't know what you would want to call it. But yeah, it's the situational awareness one.
Yeah, I'm trying to make this space not just about papers. So it may be about, last time it was about, I talked about Gemini 1.5 Pro, and this time I want to talk about this paper or book because I'm sure everyone's interested in it. Unfortunately, I didn't read whole paper because it's pretty long. So let me just focus on like the first half, because it talks about AGI. So it's not strictly about research, but it's a very exciting area. Personally, I think more engineers and researchers should more seriously consider AGI happening soon. So in the first chapter, Leo, the author, said AGI by 2027 is strikingly plausible. So GPT-2 to GPT-4 took us from preschooler to smart high school abilities in 4 years. Tracing trend lines in compute, which he said like 0.5 orders of magnitude per year, and algorithmic efficiencies also 0.5 order of magnitudes per year, and unhobbling gains, basically like RLHF, chain of thought, to use long context lengths and so on for to bring it from chatbot to agent. And then we should expect another preschooler to high schooler sized qualitative jump by 2027. So firstly, Leo is not like a conventional machine learning researcher. So he, the way he explains is a bit more casual. So, but overall, I sort of agree that AGI is going to happen like around 2027. Maybe I'm thinking of more like 2030, around then. The precise time doesn't really matter, because the definition of AGI is not really well defined anyway. And so, yeah. Also, he claims that also he listed various reasons why AGI is happening soon by citing various landmark moments and extrapolating the pace of progress from them. Here are some of my remarks. And his timeline approximately matches mine. So as I said, the definition of AGI is not unique. So I'll just pick my favorite personal definition, being able to replace the majority of machine learning researchers. And I'm guessing this may be possible around 2030. I could be a bit optimistic, but some people agree with me. I don't know about people here, though. Anyway, so he quantized the degree of improvement in each domain. So like compute, algorithmic efficiencies, and unhobbling using order of magnitude. But this is rather inaccurate because the capability of a model is determined by many dimensions. including scaling, the use of chain of thought, the use of tool, the use of LLHF, and so on. We cannot compensate for a small value in one dimension by a greater value in another dimension, as the small value dimension becomes a bottleneck. So, for example, just because you scale up, just because you spend 100 times more compute while scaling up the model optimally, doesn't mean that you don't have to use chain of thought. If you don't use chain of thought, it is not possible to solve there's math benchmark or human eval. Sorry, not human eval, but Hendrik's math benchmark. I think it's impossible to answer the final, the final answer without doing any intermediate calculations. So there, in that sense, chain of thought is irreplaceable, and likewise for all the other components like RLHF, tool use, and so on. So we cannot quantize each component into numbers, like a one order of magnitude improvement from RLHF or something like that. So that's my disagreement. But this is not his main. This does not really invalidate his main theme, which is his AGI timeline. So I will stop that. And I think more people should make their career and life decisions based on the assumption that AGI will happen soon, and you will be replaceable by then. Even if you are an AI researcher or engineer, obviously some of them will not be replaced, but many of us will be affected. Unless your job is one of the jobs that demands humans, actual humans like athletes, politicians, and some influencers. And the fact that there are few people who treat this seriously is the reason why he claimed that AGI is not priced in. Yeah, so basically that's the first chapter. Oh, yeah. Do you want to speak, or?
No, I'm listening.
Oh, okay.
I don't know what to think about AGI coming tomorrow. I don't know what to think about this, but yeah.
That's good. Sorry, it's gonna be.
Yeah, there was one question in the. I just got a question reply to the space. Someone is asking, regarding Leo's article, he seems to consider power consumption to be consistent over the timeline. However, NVIDIA claims a reduction in chip power consumption in their roadmap. Any insight here?
Oh, I'm going to touch power consumption later. I think that's mentioned in chapter 3, I guess. Oh,
okay.
Yeah. Maybe not directly addressing your question, but I think. Okay. Let me just briefly talk about it. So he was focusing on I don't know. He didn't really talk about humanoid robots, and I think that's. I try to identify the largest source of resources spent, and in my opinion, humanoid robot is going to be the most resource-consuming way of using AIs. Yeah, I will go into more details when I go to chapter 3. So yeah, that's for chapter 1. So let me just briefly go over chapter 2. So he said AI progress won't stop at human level. Hundreds of millions of AGIs could automate AI research, compressing a decade of algorithmic progress, 5+ order of magnitudes, into 1 year. We would rapidly go from human level to vastly superhuman AI systems. The power and the peril of super intelligence would be dramatic. So I think this is a very well accepted interpretation of recursive self-improvement. While some people are assuming that we are in the slow takeoff scenario of AGI, given the pace so far, I believe that hard takeoff happens when this phase is reached. We are not there yet, which seems to be suggested by Leo. But sometimes a model needs to be trained for many iterations while generating many trajectories, which can be the bottleneck on the pace of the improvement. So it's not gonna be like a instantaneously improving, like how it's depicted in sci-fi, or some people speculate. There are going to be some bottlenecks like here and there, but it's going to be very quick, much faster than current pace, just because you essentially have so many powerful AI researchers, and so so it totally makes sense. That's for chapter 2. I think. Okay, let me go to chapter 3. So in chapter 3, he said, as AI revenue grows rapidly, many trillions of dollars will go into GPU data center and power build out before the end of the decade. The industrial mobilization, including growing U.S. electricity production by tens of percent, which will be intense. So I think he may not be particularly interested in humanoid robots, but there are a bunch of people, including the CEO of Figure AI, who think that there are going to be like 1 billion humanoid robots in the future. Obviously, production of 1 billion robots is going to take a long time, but but probably not too long. And I think that's like I said, going to be the single biggest source of resource consuming part of entire system, and it's going to require many GPUs. So, and the reason why they're going to be like 1 billion humanoid is that I'm talking about like a US specific number. So in the world, I think it's going to be like 10 billion. And the reason why we think like this is that it's going to be each humanoid robot is not going to be super expensive. Like the current models are like tens of thousands of dollars, which is sometimes even cheaper than buying a car. And obviously, everyone wants their own servant robot. And given that they already own the car, and humanoid robot is going to be even more convenient than car, so I'm sure everyone wants it. And so like it's going to be kind of like mass produced like cars. And obviously these humanoid robots, they are not going to be like a state-of-the-art super intelligent AGI that only OpenAI has access to, or something like that. But nevertheless, these robots are going to be very resource consuming, because there are a few components in it. Firstly, you have to spend like the current electricity cost is like 500 watts for each humanoid robot for them to move their bodies and so on, which is pretty expensive. And on top of that, actually, there's possibly even more expensive component, which is the part that processes video input. So video input is very expensive. I don't know how it's being processed by the current state-of-the-art humanoid robots, but if you really want to try to do it using like a state-of-the-art video models, which may be required in the future, currently it is extremely inefficient and super expensive. Maybe it's going to improve, but still, I think it's going to be by far the most expensive part of AI part of the robot. So overall, I think that so right now, if you try to like feed every video into GPT-4o, it's going to cost like $100 per hour, which is super inefficient. Overall, I think it's going to be like each robot costing about 1 kilowatt. And if we have like 1 billion robots, then it's going to cost like 10 petawatt hours, or $2 trillion, which is approximately twice more than the currently consumed electricity in the US. So it's even more than what Leo predicted, Leo thought. So maybe not too far, but I think that's something we have to think about if we care about the resource, like electricity and GPUs. That's yeah, basically that's my take. Do you guys have any opinion?
Yeah, I guess like so. Those are all the chapters, I guess, or that you checked out, I guess.
Oh, that's for the first 3 chapters. Actually, yeah, pretty much these are the chapters I found interesting.
Okay.
And
Okay.
let me just briefly state other chapters. So
Okay. Yeah.
sorry, it's going to be very brief. So the reminder of the paper is just about protecting choice secrets of AGI from foreign threats like CCP and super alignment, meaning the strategy to harness AGI as well as a battle against authoritarian countries. Yeah, I don't really have much thoughts on this, or didn't have much time to go over that. I think what he said is very reasonable and standard take. I think, yeah, that's about it, I guess.
Yeah, I haven't looked at it, unfortunately, so I don't have a whole lot to say except like, yeah, I think there's a lot of extrapolation happening in this. That's what it looks like. There's a lot of extrapolation. It's unclear if those if that extrapolation, all that extrapolation is reasonable. And yeah, I don't know. Personally, I have a bit longer timelines, I guess, than this. But yeah, like honestly, I still think there may be, 1 or 2 more fundamental advances that are needed to really achieve AGI. But maybe I'm wrong.
Yeah, totally agree that there are still like a few fundamental advances required to get to AGI, especially not given that outside of at least for like any models that are publicly known, we don't know any models that actually perform well on agentic tasks. Like
right.
I'm not sure if you saw this tweet, but there was this Microsoft I don't know, top level officer person who said he probably saw like a internal GPT model or something.
Right. Yeah, I think I saw that tweet. Yeah.
Performing pretty well on like a PhD qualifying exam or something like that. So
yeah,
that's, well, obviously you can see that progress being very rapid, at least in like a academic grad school level stuff. So
yeah. So we'll see how it goes, I guess. But yeah, I'll definitely have to check out this paper in more detail. Yeah, do you have anything you want to mention or add?
Yeah, look, I think it's very hard to estimate those things, and especially giving actual numbers, like quantifying exactly when things are going to happen, and I don't know, talking about power consumption. I don't know. It's a little bit an estimate, overestimate, I think it's a spectrum. At the end, models are getting better. Everyone has a different opinion about what AGI is and what exact point you start to call models AGI, because they are superhuman already just by their being wide, and not deep but wide. I mean, no one can read and no one can know all the information that GPT-4 knows, but it doesn't know each one of them to a superhuman level better than the expert of the expert. So they're already kind of superhuman. So there is a point where everyone called the model AGI. Everyone is convinced, yes, they're just different. Everyone think AGI is a different thing. So I don't know. All the estimates about when AGI is coming, what AGI, it's a spectrum. And they are keep improving, getting better, and just, I don't know. I don't know what's going to happen in the future, especially not with actual quantifying timelines, like a year or 2 years. I don't know.
Yeah, I completely agree. Yeah, I mean, yeah, there are definitely some people saying even the models that we have right now are AGI, and yeah, personally, I don't agree with that, but people have different definitions of it, and I think the models will just like it won't be clear that there's like a single moment that, oh, this is AGI. I think it's it'd be very hard to pinpoint that exact moment. So there's also that aspect. But yeah, I think I completely agree. Yeah, it's like estimates of estimates. It's hard to make a good estimate. But I think there's still also value in some of these analysis and just kind of gaining some sense of how the progress is looking like, and just to get people's thoughts on how they're thinking about these sorts of things. Yeah, I mean, I appreciate that this paper was written up at the end of the day, and yeah, I'll definitely personally have to check it out in more detail. But yeah, I think it's still quite interesting. Yeah. Anything else you guys want to add?
Nothing. Oh, maybe we can talk about like a future plan or something.
Yeah. Yeah, I'm glad that everyone. I guess a lot of people seem to have stuck around, which is really great. This was since we missed last week, we covered maybe a couple extra papers from the previous weekend. So it probably might be a little bit shorter next time around. But yeah, I mean the general idea is like 1.5 hours or so. And then on top of that, we are trying to invite some of the authors to come and actually speak about their papers. So I think there were actually a couple papers from the past 1 or 2 weeks that we reached out. The authors weren't able to speak, so we may actually have them. We'll probably have them come speak next week. So even though it won't be a paper from between now and next week, and it'll be a little bit older paper, hopefully people will still find it interesting, and that we do have the authors come and speak. And yeah, overall we want the authors to get a chance to share their work and their research. So that's something we'll try. The other thing is we do know like the spaces is a bit limiting in terms of you cannot actually see the paper in front of you. We wanted to see if we could get a live streaming situation working in conjunction with spaces. It turns out that's, I guess, maybe harder than we thought. So we'll see if we can get something like that working for an upcoming spaces. But yeah, I think it would be nice certainly to be able to show the papers at the same time. But at the same time, I think the problem is that Spaces is much more, I think, is much more of a focus here on X or on Twitter than live streams. With live streams, it's harder to have discoverability. It's harder to have people kind of come up and speak like we're having here, like with say, yeah. And so, that's the issue with live streams. So we haven't moved we don't want to do just live streams. We want to try to do something a mix if possible. So we'll try to explore some of the options there. And if people have ideas for this, feel free to reach out. I'm happy to hear ideas about ways to set this up, or if people have other suggestions. And yeah, we of course are we posted the papers ahead of time, like when the space started. Maybe we'll try to post a little bit earlier as well in the future. But yeah, the paper list should be up there. We usually cover about, I guess, somewhere between maybe 7 to 10 papers is kind of the goal here. Depends per week, of course. Some weeks there may be more interesting papers, and other weeks maybe not many interesting papers. So it just kind of depends, but that's kind of what we expect. Yeah. Anything else, Aaron, that you want to add about our future plans?
Oh yeah. So the thing is, I tend to want to focus on like fewer papers than Tanish does. So I guess I'm gonna focus on a bit less paper, but probably like go a little bit more details at each, and also sometimes explore some non-paper like the one we discussed today, or like even maybe just a general news or something. Yeah, that's my plan. If you guys have any interesting suggestions, please let us know.
Yeah. If anyone has any suggestions, feel free to tweet at us or DM us, and we're really, I guess, we're excited to be doing this, and hopefully hopefully people are finding these spaces, or this sort of weekly thing interesting and useful. So I think with that, I think we shall end the space, unless Aaron, any last minute things to add?
Oh, nothing. So see you guys next week.
Yep. See you guys next week. Talk to you guys later. Bye-bye.